Well, hello and welcome to this month's CRC Cafe. I'm Allison Justice, and I'm very excited to welcome our guest, Alex Eckman. He is a recent graduate from LSSU. If you don't know it, it's Lake Superior State University. And he is here to share some of his work from his senior project. Now, I say that as an undergrad, study, you might not think it's going to be so in-depth, but it's very in-depth. Really, really proud of his work and excited to share it. But why don't we start out on the personal note and tell a little bit about yourself, why you chose this topic, what in the world are you going to do now that you are graduated? What's the next steps?
Absolutely. Thank you. First and foremost, I appreciate you having me on. Still got one class to finish up this summer, and then we'll be graduating. Don't really know what's in store for me after graduation. Still kind of feeling that out right now, but really excited to kind of dive into this research. A little bit about me personally. I've been in the Michigan cannabis industry for nearly a decade now. Started in 2016 as a bud tender, and then worked my way into managing extraction labs. In 2019, I saw the degree program opening up at Lake State and figured it was a perfect chance for myself to double down on cannabis as like a career. And having not had any formal degree beforehand, I figured it was a perfect opportunity. So in May of 2020, headed up to Sault Ste. Marie and started the degree. And it was really transformational. It opened my eyes to a lot of really just everything from the molecular side of things, a little bit more on the core chemistry and analytical side, which I had really not a lot of hands-on experience with, having only been in dispensaries and extraction labs. So it really got to show me kind of side of the industry that I hadn't really seen before. And one of the things that really compelled me about this degree program, I remember when I was touring, the dean had kind of mentioned that graduates would have the opportunity to do research, some of which may or may not be able to get published, or it could be stuff along the lines of creating new procedures. And that really appealed to me. So when my PI, Dr. Wright, asked me to kind of jump on this research project looking into heavy metals testing in cannabis vapes, it was something that certainly interested me. It was an opportunity to really dive into method development, kind of get into that whole creating a new way of doing things. And this was kind of based off of some early research that we had saw published showing that ICP-MS may not be a perfect means of doing heavy metals testing in vapes. And it came from a reproducibility study. So we had intended to develop a novel method with SEM-EDS. And the other thing was, before kind of getting into the cannabis industry, I was actually really into e-cigs and vapes. I had started like making my own handmade vapes, making my own e-juice for it. So I knew a lot of kind of the construction of these vapes and the history of it. And it just seemed like a perfect fit for myself and Dr. Wright. And that's really how I kind of got introduced to the study in the first place.
So you went into it thinking you're going to do heavy metal testing, and
Yep.
As we'll see in your talk here in a minute, it changed pretty rapidly based
Completely.
off of one little find. And if you would, because this isn't necessarily a chemistry audience, it's a lot of plant scientists, horticulturalists, growers. Explain to me in layman's terms what all of the letters you were just throwing at me are.
Yeah, I guess we'll start at the basics. Something like an ICP-MS is a inductively coupled plasma with mass spectrometry. It's basically a fancy instrument that's used currently to test heavy metals in cannabis products. It's what the industry uses as a standard, and it's very good at what it does. It can test down to the parts per billion, but as this recent research had potentially shown, there could be a reproducibility issue depending on particle size and morphology and stuff like that. So what we had thought we could do was take something called a scanning electron microscope coupled with EDS, which is electron dispersion spectroscopy. And basically what that is a microscope that, instead of using light or optics to really zoom in on what we're looking at, it uses electrons, kind of like a lightning bolt. And with that special kind of sensor attached to it, we can generate X-rays that are characteristic of different particles. So what that would do is essentially how we originally planned the study was we would dissolve the contents of the vape cart in a solvent, pass that solvent mixture through a filter that was 0.2 microns, so really small pore size on it, and that would catch kind of any of the metal particles that were present. The SEM, that kind of fancy microscope, we could then use to not only take pictures of the shape and size and what those particles look like, but we could then use that EDS sensor to generate those characteristic X-rays and do what's called a particle analysis and actually count how many particles we have there. So we figured that would be a really good method for potentially replacing the ICP-MS version of heavy metals testing with an SEM-based one. But as we come to find out, we ran into some issues during the sample prep that really caused us to change our focus on potentially for the better.
That is fascinating. I think now's the perfect time to pause. We'll play the video that Alex has recorded prior, and then we'll jump back into conversation.
So taking a quick look at the common hardware used in both cannabis and hemp vapes, which I should note are identical, differing only in the composition of the oil that is put inside of them, they tend to fall into three main formats. Up on the top left, we've got the traditional 510 threaded cartridge. Below that, we've got the pod style cartridge. And over to the right, we have the disposable AIO, which is short for all-in-one. And though ironically called disposable, we're starting to kind of move away from that name simply because the lithium ion battery that is present in a lot of these really aren't too disposable. But regardless of format, all of these devices include the same core components. They're going to have a reservoir or a tank for holding the oil. We can see that here with the clear polymer tank reservoir on this pod cartridge, this borosilicate glass reservoir on the 510 cartridge, and in the disposable cartridge or vape, the reservoir is actually built into the body here. Beyond that, there's going to be a heating element with a wick to actually aerosolize the cannabis oil, and there's going to be a vapor path that transports that vapor from the heating element into the mouthpiece. Now, it is important to note that we're starting to see postless vapes appear, which do not have this metal or often ceramic chimney stack going right up the middle, which could have a lot of contact or surface area contact with cannabis oil. And we're starting to see the emergence of what's called postless, and generally it follows a vapor path like I'm trying to draw out here that just kind of goes along the side of the vape, avoiding any contact or as much contact with the oil compared to these more traditional designs. Moving on into the vape materials used, most reservoirs are going to be made from either glass or polymer. Glass being a little bit more common nowadays and typically borosilicate, but polymer-based tanks are still widely used, especially in cheaper or lower-end hardware. Some of these earlier devices used ABS or polycarbonate, but those materials were phased out due to issues such as brittleness and cracking, particularly in the early days of the e-cig industry, actually. What we see more commonly now are PETG, PCTG, and proprietary PCTG blends such as Tritan PCTG. All of these are thermoplastic copolyesters, and the polymers really just differing in optical clarity, moldability, and various chemical thermo properties in resistance. As for the wick and heating components, they will often contain a porous ceramic material in a variety of metals, including iron, chromium, aluminum, nickel. We do see bismuth used as a lead solder replacement, and despite that, we sometimes still do see lead present in these vapes. Over here, we can just see a quick figure of where some of these different materials are often utilized in the vapes and how it's kind of distributed throughout the vape hardware. Now, these polymers in the vape tanks are formed through a condensation reaction between a diacid and one or more diols. Generally, we see polyesters as the main polymer being used, and those are just simply polymers that are linked with an ester bond, such as PET, PCTG, and PCTT. When we take a look at what our diacids and diols could be making up these various polyesters, we see that the diacid is almost always terephthalic acid or TPA. The diols can include ethylene glycol, cyclohexane dimethanol, and tetramethyl cyclobutane diol, among some various others. And these diols are what are going to actually drive the unique chemical and physical properties of each polymer. For example, PETG and PCTG are very chemically similar. We can see they both contain TPA as the diacid, and they both contain ethylene glycol and CHDM as their monomer diols. The only difference is going to be the molar ratio between the two, and that's what really derives the naming. When we have more of this flexible ethylene glycol monomer in molar ratio compared to the bulkier CHDM ring monomer, we get what's called PETG, which is commonly seen in plastic water bottles. Now, when we use more of this bulky CHDM ring monomer as our major diol compared to ethylene glycol, we get a slightly more rigid structure that's going to have a little bit less polymer chain stacking potential or properties, simply because there's a little bit less flexibility in that overall polymer chain, and that's going to lead to a more amorphous structure as compared to a more crystalline structure. And it's also going to play a role in its various impact resistance, thermal resistance, and chemical resistance. It's kind of why we really do see PCTG used as one of the most common polymers in vape tanks. Now, taking a look at PCTT, this is also a polymer we're starting to see more use in vape tanks, and that's because it's even further strengthening or causing a more rigid chain structure. This really bulky tetramethyl cyclobutane diol ring is going to present more intermolecular forces and change the electronic environment around the molecule, leading to those thermal and chemical resistance differences compared to PCTG. And we really see that on this slide, taking a look at the bottom right, how PCTT's structure is a little bit more bulky and going to be more rigid than that of PETG or PCTG. Remember, the difference in naming is just going to be based on the molar ratio of your ethylene glycol to CHDM monomer subunits. Really, over time, the manufacturers switched away from PETG, really again kind of in the early e-cig era, to a PCTG construction for enhanced chemical resistance and strength, but again more recently started using PCTT for further enhancement of chemical and heat resistance, simply because we're switching out this kind of flexible ethylene glycol subunit for that much more bulky TMCD subunit, which these methyl groups are going to introduce various electronic environment differences and present different intermolecular forces, along with just creating a overall more rigid and bulky structure to disrupt polymer chain stacking. Now, the original aim of this project was to quantify heavy metals in cannabis vape oils using a scanning electron microscope. And so we decided that we could simply dissolve the vape carts into a solvent, pass that solvent mixture through a filter which would capture any of the metal particles present. And then we could pass that filter under the SEM and using EDS software actually quantify and characterize any of the retained particles on the filter. But as we can see in this picture over here on the right, we quickly ran into some issues during the method development phase, as some of our vape carts precipitated out this unknown white solvent here, which was volatilizing under the SEM beam and just causing all sorts of issues. So we actually had to pause the method development here and really pivot the study. The new research objectives were to isolate the precipitant, quantify how much was present, identify what it was, and then based on preliminary patterns, our early hypothesis was that it might be a polymer leaching directly from the vape reservoir, likely related to the vape construction. Started by first obtaining the mass of the vape full, including the battery if it was a disposable. We mounted that vape upside down and simply used gravity to empty it out into a centrifuge tube, simply because we didn't want to introduce any additional solvents or heat that could cause further leaching or degradation. We dissolved it in hexane and performed vortex agitation, which reliably precipitated out this white solid that we see here. And then we went on to centrifuge the precipitant into a pellet so we could decant the solvent, wash that pellet twice, and that was really done to ensure that no cannabinoids or terpenes would be present in the end analysis. We then moved on to the gravimetric analysis, started by obtaining a mass of a dried nitrocellulose filter placed in a desiccant chamber for a couple days prior, filtered the pellet that we obtained from that last step. We removed the solvent and dried the pellet in a vacuum oven for 2 days and then obtained the mass of the dried filter and pellet. We can see here that from our sample size of 8, 7 of them included polymer construction reservoirs, and the average precipitant recovered from those polymer vapes was 4.8 milligrams, representing an average weight by weight percent basis of 0.82% when compared to the starting oil weight that we had. The maximum precipitant recovered was 9.7 milligrams, and that was coming from vape number 4, representing a weight by weight percent basis of 1.58%. Taking a look at the maximum weight by weight percent recovered, or the worst offending vape I like to call it, is vape number 5. That gave us 1.61% on a weight by weight percent basis, representing 9.1 milligrams of total recovered unknown solid. Taking a look at the microscopic analysis, up at the top, we have some various light microscopy images. Did not show us much, just that we have a heterogeneous density and a roughly amorphous structure going on here. Under the SEM, we took a look at it first under the backscatter electron detector in topographic mode and just saw a kind of rough, irregular morphology, but nothing super definitive. Taking a look in composition mode, which features atomic level contrast brightness, meaning that heavier elements are going to show up brighter. We did run a particle analysis on this little speck that we see here in the middle. That was actually a aluminum particle, which was interesting to note. Beyond that, though, we do see some fracturing going on within the particle. And switching over to the secondary electron detector to get a better look at the surface morphology, we really get a nice look at what that crack looks like there. It is kind of important to note that the stub rotated in the SEM, so that's why this is on a little bit different angle. But overall, just didn't really get a ton of definitive information for identifying what we could have based off of either of these. Moved into analyzing the unknown's physical properties, we started with melting point, which showed a broad melting point range, which is kind of typical of copolyesters, but it is important to note that we utilized a melt temp apparatus simply because that's what we had available to us at the university. Ideally, if I were to do this again or in the future, would use thermogravimetric analysis or DTC to accurately determine the melting point range, but more importantly, the glass transition temperature. But again, just working with what we had. So we move on to the solvent testing, just trying to see what it would dissolve in. Have a range here from polar on the top left to very non-polar on the bottom right. You can see that it really didn't dissolve in anything except chloroform, which was actually good because we needed that to perform further spectroscopic analysis down the road. Moving into the ATR FTIR spectroscopic analysis, the spectra actually appeared really nicely matching up with what we found in literature for PCTT. Over here on the left, we've got the wave numbers from our sample compared to the wave numbers from that literature that we found. And again, it is just really close in inverse centimeter wave numbers. Over here to the left, though, what I did was I took a spectra of our FTIR and then just annotated over it some of the key stretches that were utilized in really helping us determine that this could be PCTT. Do want to note real quick that all of these would be repeated throughout the chain, but I just simply didn't include some of these color matches for simplicity's sake. Wow, I'm struggling today. Anyways, so this like carbon, oxygen stretch that we see right here correlates to this peach kind of tan color on the structure, but it would also be present in this ester linkage, and this ester linkage just didn't want to muddy up with too much color. Moving into Raman IR, this was actually done in 2 stages. First, Nicholas Gordon from Lake Superior State University ran a preliminary Raman scan using our system, but ultimately we worked with Dr. Vernon Lalone, who ran a much higher resolution analysis using his own Raman setup. And at this point, we didn't really know what we had. This was kind of done in tandem with that IR analysis. So what we did was we sent him 2 samples of the precipitant that we recovered. That's named slide 1 and slide 1A on this figure. But we also sent 4 exterior samples that were scraped from the outside of the vape tank. And we can see here that a lot of our peaks really closely line up, with the exception of these 3 unique peaks that are identified with the arrows. Those are still yet to be determined. Ultimately, this did help kind of point us in the right direction, that what we had precipitating out from the inside really closely matched what was present on the outside of the vapes. Going into then the NMR analysis, this is how we really definitively were able to say that we have what we think we have. Just looking at the carbon NMR here, what I did was simply just overlay the structure with the assigned peaks correlating to the assigned atoms on the structure. But we used a whole host of NMR to really come up with this. That was carbon NMR, proton NMR, HSQC, DEPT, and COSY. So by combining the 1D and 2D NMR, we were able to really come up with this nice table, which features our hydrogen NMR here on the left, carbon NMR on the right, and then this second column here where it says reference from literature on both these. This was actually a published study looking into altering the PCTT structure with various ethylene glycol or isopalic acid monomers to really see what it would do to the end characteristics for 3D printing filaments. And as we can see here, when we compare our chemical shifts to the chemical shifts noted in that study, we again, just like the FTR, come very, very close in what we actually saw compared to what they saw. But really more importantly here is we've got this absence of peaks, where the reference literature showed peaks present for ethylene glycol and that IPA monomer. We actually didn't have that. And that kind of let us know that we potentially have a neat or pure PCTT polymer instead of some potentially proprietary blend like we do see with the Tritan PCTG. Really then we were able to present some conclusive evidence for PCTT leaching in cannabis vapes when we put all of our analysis methods together. On the top here, we see the structure that we propose for what we found to be that unknown precipitant leaching in our vape carts. And that structure is that of PCTT, or better known as poly-1,4-cyclohexylene dimethylene 2244 tetramethyl 1,3-cyclobutane-diol terephthalate. Now below that, this is the structure of that modified PCTT structure that I was just referencing from that 3D printed study, and that features the ethylene glycol unit as well as that IPA unit. Again, we did not see this in any of our vape carts. We do believe that we have this guy up here at the top. So then moving forward, suggesting a plausible mechanism for this degradation and leaching. Well, we know that terpenes can act as a solvent. Beyond that, one of the things that I noted was that contact time seemed to be a driver for leaching, with most of the worst weight by weight percent leaching cartridges appearing after about 700 days in age. Right around 2.5 years is about as old as our vape carts got, according to manufacturer provided batch data. However, it is important to note that we did have a small sample size, so would love to do some further shelf life testing to really see if it is contact time or terpenes causing this, or potentially even a little bit of both. And then just as a final note, of course, would like to acknowledge Dr. Derek Wright, Dr. Vernon Lalone, Nicholas Gordon, Dr. Adam Mosey, and Jackson Runn for assisting with this study, and would also like to mention that the SEM-EDS imaging was performed at the Microanalysis and Spectroscopic Characterization Lab at Lake Superior State University, and that was all made possible with funds acquired through an NSF grant. We can see the award number down here at the bottom, but just would like to once again acknowledge all these people and thank them for the immense amount of help that they provided over the past 1.5 years as a part of this research.
So, Alex, that was a lot in a good way, but certainly way over my head as far as all the plastics and polymer types and everything like that, but incredibly important and incredibly useful and work that, you know, like anything else in cannabis, we're just going to have to keep building on it and building on it and building on it. But if I'm looking at your work right, the takeaway is somehow this one type of polymer, the PCTT, is somehow coming out with your solvent. And the fear is that terpenes, which are chemically a very similar size and shape to hexane, which was your solvent, might be causing this polymer to then leach into the oil. But that might be the end of the story, because it might not actually transfer with the oil. Those are all big question marks, right?
Exactly.
But you know, what's your hypothesis? Do you, knowing its molecular weight and other studies that maybe have been conducted, you know, do you think it comes through? And have you stopped smoking vapes?
Yeah, so first and foremost, I'd definitely say that all this data is still preliminary. We're still pending peer review on it, and would definitely love to do future research on this to really determine if it is the terpenes or something like contact time driving it. Since a lot of the vapes we noted were around 1.5 years, 2 years old. And so there's certainly the potential for age and shelf life testing being a driver for the leaching. But as well, like you had mentioned, we have noticed and we've got published literature showing that some of the terpenes in cannabis can act as a green solvent similar to hexane. And hexane being a pretty good overall solvent, I mean, it's not unplausible that that could be a potential driver. I'm definitely looking forward to see if it's a certain terpene that's causing it, potentially one or maybe a mix of terpenes, or if it's something like the concentration of the terpenes playing a role. That's all definitely future research that we're going to have to do. But I think definitively we were able to say that we do have a measurable amount of these polymers leaching, and that was evident by that rough gravimetric analysis that we did, although I would love to repeat that with a much larger sample set size. However, I mean, with a maximum of 1.6% weight by weight by volume, that's definitely something that was alarming to myself and was cause for me to, that was definitely a driver for me to kind of switch away from vapes, even though this was a preliminary kind of study. We had noticed in that early method development using the SEM that there was also a lot of metals coming through, as well as silicates, which was certainly cause for concern in future research on glass cartridges too. So it may not be that just polymers are faulty. It could be that many different types of vapes and constructions construction type, could have issues. And so for me, I was personally only really using vapes here and there for convenience. So it was easy enough for me just to switch full on concentrates and use a Puffco. So for me, yeah, that's what I use. Is I just use a Puffco or a dry herb vape. Occasionally we'll smoke some pre-rolls or use some edibles. But yeah, myself, I've come to stop using vapes for the time being, but definitely would love to dive into this research more to see if any of these microplastics or polymers actually enter the vapor stream, because we've demonstrated that they can leach into the distillate or the live resin, but we don't know if it then goes into the vapor stream to be inhaled.
Right.
That's something we're currently trying to get, like a vape machine or a smoking machine similar to the combustion machine that you guys have utilized in the past, so that we could try and perform that type of research down the road as well.
Yeah, that's incredibly important. You know, as disappointing as it is, you know, the more science we do, the more we understand what, you know, dyes in papers do, what types of vape cartridges do. Yeah, it definitely kind of shortens your options of what, you know, you now understand as safe, right? People are going to vapes because they think actually combusting, you know, dry flower can cause carcinogens, but then it's like, well, once you give
Right.
time and resources for research to happen on these vapes, well, what's happening with those vapes and that, you know, could be detrimental. So, yeah, you got to kind of pick your best choice. That I got there. There we go. There's a good question. So if you did have to vape out of a vape cartridge, you know, you don't have to necessarily name a brand, but which type would you choose?
So we even tried like the postless ones, and even those picked up some particles. I will say there is one type of cartridge that I haven't been able to get my hands on to test yet, but it's called the Quantum Vape cartridge. And it's almost kind of like that Puffco design. And if I understand the construction correctly, it kind of heats the oil up, and the oil drops down using gravity onto almost like a ceramic plate, similar to a Puffco 3D XL coil, for example. And something like that I could see potentially being better, but even then it comes down to the hardware specifications and tolerances during the manufacturing process, where these are being constructed and made, and you know, if it's overseas or being done in bulk, how good is their quality control, quality analysis to make sure that they're really removing all these particles. Because that's one thing that I also learned in the method development, is just how incredibly hard it is to get a zero particle blank, and just how thoroughly clean everything has to be. So I can only, you know, I completely understand how, if they're mass producing these and pumping out hundreds of thousands of them a week at the hardware level, not necessarily the manufacturer and putting the distillate in it, but just at the main supply chain level, it's understandable that particles are going to come through. I guess the question then is, what particles and how much do we deem as okay? And again, I think that's subject to future research. Something like those glass cartridges leaching the silicates was certainly something to be concerned of. And honestly, I don't have enough background knowledge on that. It's something I'm excited to kind of dive into deeper down the road. But I mean, it just goes to show that really on the vape cartridges side, I think the jury's not yet out on what the most safe is. I would say personally, I would stay the farthest away from the disposables that have the polymer walls on it and have the most surface area potential for contact, especially if it's like a 2 or 3 milliliter vape cartridge.
Yeah.
Those ones, and if it's been sitting on the shelf for a while, I would be a little bit cautious of. But yeah, I don't know if I could really recommend one, just simply because I haven't had a chance to test those new quantum vapes. But just based off of the theory of the construction, I think that would probably be the best.
Okay. That's a good tip.
And certainly just finding small volume, like those 0.5 milliliters. I know we kind of phased them out as a industry, but 0.5 mils or 0.5 grams, whatever you go by, and just finding the freshest that you can so that you have the least amount of surface area contact with anything, whether it's polymers, glass, or metals, and then the least amount of contact time.
You know, microplastics and, you know, that concept itself has entered the news and, you know, is getting a fair amount of recognition now. Can you explain, you know, the difference between polymer, microplastic, plastic, you know, just give the audience a little idea of how those all relate?
Yes. So first and foremost, I should say, before I dove into this, I was definitely more interested on the organic chem and med chem side, and this kind of forced me to become a polymer chemist. So I'm no expert by any means, but really what we look at when we try to define these terms, polymer is really kind of like a Lego block chain of these things called monomers, and they're kind of the individual building blocks of that plastic. And when we get down below a certain size, being 5 micron, that's where you start entering that microplastic region. So it really comes down to particle size. And then the different polymers are really just different substances, whether they're polyesters or polyamides, that's also known as nylons. All these kind of things, they can be synthetic, kind of like those polyester, the shirts that we wear, or they could be biological, like DNA is essentially a polymer. It's a repeating chain unit of all these different kind of building blocks. So they can be natural and they can be synthetic. They're found all over. And it's definitely a very wide class of chemistry, as certainly I've come to learn.
Yeah, so it's very intriguing to know, you know, to understand, are these actually transferring through the oil? And like I've told you before, if we can help at the CRC with, you know, donating the combustion for certain sects of time, because of course we have to use it too.
I really
you know,
appreciate that.
We want to try and help as much as possible.
Thank you so much. I really appreciate that.
For sure, for sure. Well, that's, you know, that's what we want to do is lift up research and researchers like yourself, and, you know, get the information out there as much as possible, because, you know, we're all doing this because of a love of the plant, whether it's extraction portion, you know, we all have our sects that we love, but they all relate in some sort of way. You know, the strains you asked me to grow, which maybe have these 2 terpenes that, you know, we know can break down these polymers, maybe I avoid growing those for my vape manufacturer. So it all relates, and, you know, I think all of our work needs to be lifted up and shared as much as possible. So thank you so much for coming on and sharing your work and showing us what you've done. It's absolutely excellent, something you should be proud of. And absolutely, when I imagine once you're through all the long, hard processes of peer review, you know, absolutely send it to us, and we'd love to share that.
Will do. Thank you again for having me on. I really appreciate it.
Yeah, thank you.